Today we are talking about the paper AI methodology for investigating AI patterns prevalence in software repositories. I come from a background of open source and distributed system research. So with the AI, with the large language models, it's much easier to build AI applications. And a lot of us are using AI as part of our application. So then at the same time, there are a lot of work on AI patterns has been done. And so there are a lot of AI patterns that has been proposed. As we will see, there are actually hundreds of AI patterns proposed. But which of them are actually there? And how can we find which AI patterns actually being used in code and helpful? So goal of our project is trying to find that, trying to look at code and to find which AI patterns are being used. If we can find that, those will be useful to find important patterns. It will give clarity to developers, and we can verify the candidate patterns as actual patterns, etc. There has been a lot of related work on this bit and AI patterns, and so there are a lot of articles, etc., from developers and practitioners about AI patterns. There are RAG AI patterns, there are agent AI patterns, and there are a lot of work on pre-LLM AI patterns, etc. So taken together, there are hundreds. And there is a lot of work on pattern mining from code. So the initial work, they focused on basically using search-based approaches. That means they will look at the code, look for patterns. The approach switch into graphs. So that means they will take the code, represent it as a graph. One approach use classifiers. You will look at the code and you will extract features and build a classifier to see whether this code has this pattern. Those machine learning based approach evolved into using embedding. Embeddings is that you don't have to do feature engineering anymore. The embeddings is numerical representation of the code. For example, this Pandey et al. Will talk later, which is very recent approach, which did very well detecting patterns within. And there are several benchmarks for pattern identification, PPAR, DPP, etc. But they mainly focus on the base of engineering patterns for detecting AI patterns. So as we said before, the problem we were focusing on is that how can we find which AI patterns are actually there in the real world. So we propose this methodology for doing that, which we will go through in next few slides. The first step of the methodology is to go and identify what are the proposed AI patterns. Second step, we go and find representative 100 GitHub repos that has AI application. And then from these repositories, we detect what we call the code communities. We will discuss that later. The third step is to build a model to identify these pattern classes we identify on the step 1. And we build this model. So now remember, we don't have training data. So we build this model using active learning approach by we basically manually label these pattern, these code communities, 100 at each iteration, then build a model, use that model to predict, then look for we do margin sampling. That means we look for where the uncertainties are and relabel 100M, and we iteratively go around and when the model is good enough, we go to step 4. We use this algorithm for prevalence prediction using the forecast from a model. So basically now we have a model to detect how many patterns were there. Then there's a way to go from that model to the estimation of real frequencies. That's the step 4. So we will walk through each of them in next few. Okay. So the first step is we selected these 20 papers, articles, practitioners, sources, etc. that propose AI patterns. Then for each of them, we use LLM to extract pattern candidates from this graph. You can find the prompt link from the paper. Then for each of the pattern candidate we identified, we generate word embeddings. And then we took all these candidates and took their embeddings and used dbScan to cluster them. So the expectation is that the candidate patterns that sounds very similar would come into the same cluster. So we found about 300 pattern candidate clusters. Then we manually went through them and grouped them into 14 pattern classes. So the way we did this was we first start with about 6-7 pattern classes and try to group the non-pattern candidate classes into this. But if we see a recurring pattern class that's not included in the list, we added that. Like that, we end up with 14 classes. So these are those classes. And you can see that a lot of widely used concepts from the AI is represented there. So that is the first step. Now we went to the second step, which is to find 100 code repositories to represent AI application. We went to GitHub and we looked for the repositories. We selected 100 Python repositories which has stars between 250 and 1000. What we did was we used different filtering criteria and trying to manually inspect. What we found is that any repos that has more than 1000 stars, they are usually framework like TensorFlow, etc. But we were actually looking for how people build AI apps, not people build AI frameworks. So by trial and error, we found that 250 to 1000 stars are a good place to look for AI apps. Then we filter, get the list, go through and manually, but by manual inspection, we selected 100 repositories. And the selected ones we manually verified and make sure it is actually AI related. So then, now when we get a repository, we are trying to go and detect AI patterns there. Now, repository is too big to detect an AI pattern. So we need to break the repository into small parts. And so we tried to actually first break it by files. That didn't work. We tried different things that didn't work. But finally what worked was that building a call graph for that repository and using a community detection algorithm, think it as a clustering algorithm, to detect the code communities. These are code that set of functions that are closely related to each other. And that actually gave a good basis for detecting patterns, as you will see on the result. So what actually happened is we ran through this full pipeline several times using different methods, but it is using these code communities, detecting code communities that worked. So then we came to step 4, which is we build a model. Let's go in. What we did was, now remember for each repository we have identified code communities. We first started by, so we have two things. We have code communities and embeddings for these code communities. We have 14 pattern identified. We first gave these 14 pattern classes each of them to LLM, ask it to generate sample code. Now, from the generated sample code, we first build a model. And using that model, we try to predict which pattern class. So there's another class as well. So there is this 14 pattern classes and another class. So each code community, we say, predict this. So then we look at the model and see which predictions where the model was least sure about. This is called margin sampling. And those cases we manually looked into. We took 100 samples, we looked into that and manually labeled them with the help of LLM, but these are manually labeled. Now we have 100 data points that was manual labeled. We add it to our training set and retrain a model with 5-fold cross-validation. And when the out-of-fold accuracy, we look at the out-of-fold accuracy. And using that model, again predicted on the non-labeled data, and again look for most uncertainty, iterative. So at the third step, actually, after 3 iterations, we try removing that initial generated data from the LLM. We figured out actually just keeping the label data is better. Adding this LLM generated data reduce the accuracy, so we removed that. And after that, so we ran through this iteration, and we got this results. So there's one more comment. Out of these 14 classes, we dropped 7 because on the label data there were too small samples for those classes, and we basically put them under none. So you can see the result. So now we have 8 classes, which means the random chance for the prediction is 11%. We got 55% F1 score. Okay, so that is much better than the random chance, and you can see the verified data on the right hand side. Now coming back, what we actually need was, now we have a model. This after 4 iterations, we have a model that has 51%. Now we have a model, but what we really need is we need to know how many actually for each of this class, how many patterns may be actually out there. Now it turned out it's a known problem with a known solution. It's called prevalence estimation. If we have some equipment or a model to test some property, now that model has error too, and if you go to the world and do a random sample and collect data and apply the model, there is a way to estimate actual number considering the model's confusion metrics as well. So what we did was, now we have the model. Now we take all our code communities, right, and forecast the frequencies using that model. And those forecasted frequencies, I'll call them OD. Then, now there are 2 kind of errors. There are errors due to this model's failure, which we estimate by using confusion metric. And there is a sampling error because we are only looking at a smaller. So the process to handle these 2 errors is we define a multinomial distribution with OD as the initial frequencies. Then we sample from that distribution, and for each sample we do an inverse calculation and calculate by solving the linear system. In the right hand side, we estimate actual true frequency. Now this is only a one sample. Now to understand the variation, we again resample the multinomial distribution 20,000 times, and from that we can get a we can get a distribution for the true frequency. So this is the algorithm. This is in the paper. You can look at that. And so this shows the results, right? For the these 7 pattern classes, you can see the confidence, the true frequency distributions. So there are a few interesting things. Now each data come with the error bars. So that means if the error bars are too wide, or like for example, if you consider C4 and C7, sorry, if you consider C4, C7, they can be 0, 2 based on these error bars. So the error bars tell you which patterns you cannot trust, which numbers. And then other ones, for example, if we look at, we can see very clearly that C3 and C2 has much more higher occurrences than the C1 and C6, which has better than C4 and C7. So we can get an understanding of relative error. And the fact that there are error bars means so some pattern classes, we might see that the estimate is weak and we can't rely on that. Now, if you want tighter error bars or more pattern classes, you can try to run our methodology for more iterations, and likely it will give you better results. However, because we are not picking data to label, we are labeling data based on the active learning answered calculations. We cannot control which pattern classes we are labeling. So basically, we had to run through the process and see what is in that. So this gives us a way to estimate the true frequencies of these pattern classes. It is wide but still usable. Then we actually look at the code of some of these pattern classes and see. We saw that a lot of well-known sample sub-patterns are under these pattern classes. For example, you can see agent architecture, etc. These details are in the paper. You can look at. As to come back, and human in the loop annotation, limited human in the loop annotation, and active learning to to identify patterns without having labels samples to start with, right? So that means you can. We actually think we have still done work only on the AI patterns. We think this approach can work for other patterns too. So our first contribution is the methodology. Second one is although Pandya etc. has done classification on top of embeddings to detect patterns, you have the code that is nicely identified to include the patterns, and using the community detection on call graph. So we figure out a way to how to break the code into the chunks so that we can identify patterns clearly using embeddings. So that is the second contribution. The third is we use the prevalence estimation to estimate what are the true frequencies, right? So we identified 769 pattern candidates and defined 14 pattern classes and estimate their prevalence using 100 open source repositories. Thanks very much. Hope this was useful. If you have any questions, please send it. Thank you.